Okay, let's look quickly at the physics of a very basic Atwood machine. And we'll do like an idealized situation. So, I mean, I don't think this is exactly what the original Atwood machine looked like. It was actually quite a complicated unit, but basically what we can do with an Atwood machine is we can investigate some interesting properties that you might see during some physics problems, or to illustrate how certain relationships in physics occur. Okay, so let's imagine we have like a little cart, and man, those wheels should be the same size. There we go. Okay, so we got a little cart. Nope, don't like that either. Really struggling here to draw a cart. Okay, there's my cart. And we're going to put like a pulley here. So this represents a pulley that can spin around. Okay. And what we're going to do, put a little attachment point on here. What we're going to say is that we are attaching a rope. It goes from the cart over the pulley, and we can hang a mast from here. Okay, let's put some numbers in here. So let's say this cart has a mass equal to 1,450 grams, and let's say we hang a 10-gram mass here. And although in real life you wouldn't be able to get a friction-free scenario, in this case, let's say there's no friction. And you might be asked to calculate or predict the acceleration of this system. And people often seem to have trouble with this, and I think maybe the issue is confusing which way forces are pointing. All right? So the first thing to identify is you know, we got to talk about what forces are active here, okay? Oh dear. So what we've got is we've got a mass on the cart, okay? If we look at the cart, it's got gravity acting downward, and it's got a normal force acting upward. In real life, there'd be some friction, but we're going to ignore that for now. We'll cover friction in a later episode, okay? So in other words, if this is sitting on a surface that is friction-free, any force that acts on it will cause it to accelerate, right? So with Newton's law, if no other forces are acting, then whatever net force we have, whatever force we have, will cause an acceleration, right? If there's no friction, the only force we need to think about is the force of tension in this string, okay? So how do we calculate the force of tension in this string? Where does it come from? Well, it comes over the pulley. It's caused by this. It is 10-gram mass. So 10 grams, we're going to do our work in terms of kilograms, right? So we've got to say that's 0.01 kilograms, right? Divide that by 1,000. And 0.01 kilograms is acted on by the acceleration due to gravity. So we can say then that Fg over here is equal to m times g, or 0.01 kgs times the acceleration due to gravity. It's actually 9.8, but just to make this easier, I'm just going to throw in 10 for it. Is that okay? So we'll just say that we've got 10.0 meters per second squared down. I mean, technically it's 9.81, but just to make the math easier, we'll do that. Okay, so then we get, this is equal to 0.1 newtons. All right, now this is the only net force on the entire system, right? There's no other force. There's no other left and right force anyway acting. Okay, what's going on is we are applying a 0.1 Newton force here. The pulley serves to change the direction that the force acts at, right? So the tension in here will tauten up as soon as we, you know, if we have nothing on here, this will kind of hang loose. We're going to assume that it has no mass. I mean, in real life, it would have a bit of mass, but we're not going to get into that. So we'll just assume this string has no mass. If we have nothing hanging on the end of it, we would just have like a limp rope and nothing would happen. The second we hang this weight on, we get tension here, goes over the pulley, and here. So in other words, the tension downward, the 0.1 Newton pull downward, gets transferred to a 0.1 Newton pull in this direction. Okay? Now, this is the force for the entire system. So to be very careful of that. So what we could say then is that F net equals MA. We have this for the entire system. And this system consists of mass 1, the heavy mass, and mass 2, the little mass. So the net force that we have, that 0.1 newtons, has to act to accelerate both of these masses. Okay? Now if I cut the string, right, the force of gravity would cause us to accelerate down at 9.81 meters per second squared, right? But because there's a tension in here, essentially what that means is this is experiencing some upward force. Okay, I'm not going to get into that so much. It's easier to just explain it in terms of the force on here has to move the whole system. But just keep in mind that if I were to cut this, it would accelerate downward at 9.81. Okay, this system will accelerate at much less than that because that force down here has to move this large mass as well. Okay, so the total mass moved by this force, by this 0.1, is that 1,450 grams plus the 10 grams for the little weight's got to be worked on as well. And we get 1,460 grams, which is the same as 1.460 kilograms. So if we want to know acceleration, we have to take F equals ma and we have to solve for a. So a, the acceleration of the system, is equal to the total force acting on the system divided by the total mass of the system. So m1 plus m2. And in this case, we figured out that the net force was 0.1 newtons and that the total mass is 1.460 kgs. And let's solve for acceleration. We get 0.07 meters per second squared. Now, what a friction-free system says is, no matter how large this m is, and no matter how small this m is, there's still going to be an acceleration, okay, in a friction-free world, all right? Even if this was 1,000,000 tons, and this was like 1/1,000,000th of a gram, in a perfectly friction-free system, there would still be an acceleration, okay? In real life, however, there's no such thing as friction-free, right? There's friction on the bearings of the pulley. There's friction on the bearings of the wheel. I mean, there's things like air resistance and so on, all right? But in an idealized world, no matter how small this is and how large this is, there's going to be an acceleration, okay? If there's no mass here and this is a perfectly level surface, that object will just stay still on the surface, okay? Alrighty, that's an Atwood machine with acceleration. A little bit later, we'll say, well, what if you have an Atwood machine with some friction, okay? And it's moving at a constant velocity. If that's the case, then whatever friction we have, okay, if it's at a constant velocity, must be exactly equal to this force here, okay? So in the case where the friction and Fg equal out, we could have one of two situations. We could either have the object still, just sitting there with no net force on it, or moving at a constant velocity, right? Still with no net force on it. Okay, so in the real world, that's maybe a more likely situation, that you might have like an even force down to friction. Okay, and you might be asked problems with that. I mean, it's not that hard to understand, but we'll get there eventually.